Our next speaker is Benjamin, and from KTS Royal Institute of Technology, and he will talk about top polynomial and split matrix. Please.
Thank you very much. Thank you for having me. Yes, I will talk about two things Graham just mentioned. So the top polynomial, and we should look at minors, and I will do that during this talk. So let's just dive into it. So probably all of you have seen the top polynomial, but one interesting property is you can evaluate it and get many interesting invariants of your graph or matroid, right? Like the number of spanning trees, or in case of a matroid, the number of bases, or if your graph is disconnected, you have to take the spanning forests, or the number of totally cyclic orientations, and even things like the chromatic polynomial, which the first time you might hear about this, you need the vertices, but it's an invariant of this Tutte polynomial and the specialization. So I'm interested in this talk in the Tutte polynomial. And to bring us all on the same page, maybe I don't have to say too much about a matroid, but I will use the perspective we have seen earlier this week of matroid polytopes. Okay, so your bases, by taking indicator functions, will form the vertices of a polytope. If you take the convex hull and the edge directions, they will be all of the form EI minus EJ, so in the root system of type A. Okay, this is just for one little trick, but don't be scared by the convex geometry here. And then the Tutte polynomial, so formally, as you might have seen, is a polynomial in two variables and measuring somehow by the exponents the co-rank and the nullity of a set. And it has wonderful properties. For example, if you take the dual, you just switch the two variables. That's how it's constructed. And of course, famous theorem by James Oxley and Dominic Welch, both mentioned a couple of times already this week. If you have an invariant on some subclass of matroids, which respects deletion and contraction and also direct sums, then it's an evaluation of the Tutte polynomial, and you just need to know what happens with a loop and with a co-loop. Okay, so maybe something that not all of you have seen with the Tutte polynomial, it's a special invariant, and it's a valuation. What does that mean? So evaluation, it's a general concept. So I broke it down to polytopes, but you can have it for arbitrary convex bodies. It's a map which transfers geometry in the sense of convex geometry into an abelian group, so into an algebraic structure. So it's a map from polytopes into any abelian group that you like. And for us, the polytopes, of course, will be matroid polytopes. And you don't even have to consider the polytope. It's enough if you have the information of the polytope. But what is evaluation? It has to fulfill one property. So not every function into a group will be evaluation. But if you have two polytopes, it might happen, you can be lucky, that the union of these two polytopes is again a polytope. The intersection of a convex set is always convex, so this will be always a polytope. And then you want this one equation. So you want that the valuation of the union plus the valuation of the intersection is the same as the sum of the valuation of the two original objects. Okay, and just to clarify my notion, so sometimes I will consider valuations on all matroid polytopes or all matroids. I will indicate this with this M. And if I specify the ground set, I will put an index n. That means the ground set from 1 to n, or a ground set of size n, whatever you prefer. And if I also specify the letter k, means I fix also the rank. Okay, and a prime example, the one that we already saw this week, is the octahedron. So the uniform matroid U24 gives you the octahedron. And you can split this into two polytopes. So twice the Egyptian pyramid. So it's a matroid polytope of rank 2 on 4 elements with just 5 bases. And this little square, it's U12 plus U12. And for example, if you want to know the volume of these things, then the volume of the octahedron is 2 over 3. The volume of the Egyptian pyramid is 1 over 3. And the little square is lower dimensional, so the volume of it is 0. And It's not hard to see that 2 times 1 over 3 minus 0 is indeed 2 over 3. So the volume is such a valuation. Not the most interesting one, but for us, interestingly, the Tutte polynomial is another of these valuations. Right? So the Tutte polynomial of U24 I can express as twice the Tutte polynomial of my matroid M minus the Tutte polynomial of U12 times U12. Okay. Any questions so far? Or are we all on the same page? Then let me introduce one more complicated valuation, but don't be scared. Not so important what the valuation actually is. We just need its nice property. It's called Dirksen's G invariant. Was also mentioned earlier. And what is it doing? It kind of counts in the picture where we had these blue and red edges in the lattice of flats. It counts how often or you use in which order blues and red edges to move up from the bottom to the top. Right, so this is encoded in this object, and your group is symbols for counting at what positions you use the blue or red edge. So whenever the rank goes up or not if you add a new element. And you collect all that and you get this nice invariant. And why is this invariant so special and so important to us? Because it has this universal property, meaning whatever other valuation you have, I can find a homomorphism from the group which is the symbols, this UN, to your group, which if you concatenate, gives you the valuation you are interested in. Right? So you can always take the detour from to get your valuation, taking first the G invariant and then linearly specialize to whatever value you are interested in. Okay.
So does your group G here fix group or for all group?
That works for, the group G comes from your invariant, right? So you take some relative invariant F, which maps from the matroids into G.
Ah, okay.
That's the G that you have to use.
Understood.
Okay. So we would like to have this property, let's say, for the Tutte polynomial, but of course that won't be true. So therefore we have to restrict on the left-hand side the matroids for the question to do. So I want to find the relative, I want to fix, in this case, the Tutte polynomial, and I want to figure out how do I restrict or have to restrict my set of matroids, let's say, to a minor closed class, such that if I have this restriction, every valuation, whatever you come up with, is a specialization of the Tutte polynomial. That's what I'm interested in. So whatever invariant you have, whatever relative invariant you come up with, you can play this game. You can ask yourself, what is a minor closed class such that every other relative invariant is a specialization? And I will do this game for the Tutte polynomial, and for some technical reason, which makes the proof and everything works much nicer, I assume that my class is not just minor closed, it's also closed under duals. Okay, and examples why this question makes any sense is the G invariant is of course universal within every class. So whatever restriction I would take, it would work. But if you think about the Tutte polynomial, and I give you the Tutte polynomial of a uniform matroid, then you can even tell which uniform matroid that comes from, right? I mean, the Tutte polynomial encodes the rank and also the size of the ground set, so you know exactly what the input was, so you can recover actually more, you can recover the matroid, so this would be another class, or if I restrict myself to uniform matroids, you surely will be universal on those. Okay. Here is a class coming out of the clue, but here's a nice and interesting class where the Tutte polynomial is universal within. So a matroid is called an elementary split matroid in this talk today. If you have one excluded minor, and that's a loop, a co-loop, and U12, you take the direct sum and exclude this from your class. This will be a nice family of matroids. It's called the class of elementary split matroids. had been studied before. It includes all paving matroids, therefore we assume it's pretty large. And some experts on them are here. You can ask myself, of course, on split matroids, but also Tamash is here, so feel free to ask him about elementary split matroids. And they have wonderful properties and characterization. So elementary split matroids you can get by generalizing the notion of relaxation. So instead of just having circle hyperplanar relaxation, you expand this and to something is called relaxations on stressed subsets. And if you relax all the stressed subsets of your matroid, then the matroid feels good and becomes a uniform matroid whenever you started with an elementary split matroid. And another thing which was mentioned at the beginning in the first talk by Graham, so if you look at the lattice of flats and you look at the proper cyclic flats, so excluding the entire set and the empty set, you are left with a clutter if you have an anti-chain if you have an elementary split matroid. There is this keyword elementary. If you remove it, there's also some other family called split matroids, which is very close to this, but then you have to be a little bit more subtle with the disconnected matroids. And these matroids have nice properties, like they are closed under duality, closed under taking minors, and also closed under taking truncations. Okay, so this is the first nice class. And I will demonstrate with two tools how we see that this class actually is universal within. So if I restrict to this class, the Tutte polynomial will be a universal valuative invariant. Okay, so the tool, I should give you an example, sorry. So for example, if I take this description, so it's the polyhedral description of a matroid, but if you're familiar with lattice path matroids, it's this kind of lattice path where you have one inner point, so you go north, then to the right, and then to the west, and at some point you start again walking north. This gives you an elementary split matroid, a very special one, which is also Schubert. So the Schubert elementary split matroids will play an important role. If you want to count them, it's quite easy. You can have this inner point wherever. So that's k times n minus k of them. But if you put it on the boundary, they will become all the uniform matroids. So there's one extra. That's how you can count them. Okay. So my two tools is I want to compare with the G invariant, which I know is universal, right? So the G invariant, I mean, it maps into an abelian group, yes, but this abelian group is also a Z module. So I have extra structure, and I can talk about the rank. And I can compare that rank with the rank of my invariant if I also map into a Z module, right? So that's why I now go to 3 Z modules. But a polynomial ring is a Z module, at least if it's a polynomial ring over the integers. So for the Tutte polynomial, I can apply this little tool. And I will use another tool that I developed in a longer paper with Luis Ferroni, which tells me how to evaluate, if I have a valuation, how can I get it and express it for elementary split matroids. And it's in particular simple. So another feature of elementary split matroids. I just need to know what happens on the uniform matroid. And then on these matroids that I call lambda, these were these Schubert elementary split matroids, right? So pretty easy and very few matroids. If I know what's going on there, I can express in terms of these stressed subsets what the valuation is of my original matroid. Okay. I don't want to go into the details what these stressed sets are, but these are very special cyclic flats. Okay. These two tools together already give me what I'm looking for. So the Tutte polynomial is universal within the class of elementary split matroids. Why? I just look at the image of elementary split matroids, or their Tutte polynomials. I look at their rank. I find k times n minus k plus 1 of them, which are independent, not so hard. And I do the same for the G invariant and see that there are also k times n minus k plus 1 of them. And that gives me already this result. And if you look a little bit closer, then you will see you can express every Tutte polynomial of whatever matroid uniquely as a linear combination of those. And there are more classes where you can do this, play this game. So let me quickly introduce them to you. So you can do this with graphic Schubert matroids, meaning you exclude the minor U24. and the direct sum of U12 and U12, you will come up with a graphic matroid, and everything, the two theorems will hold. And it looks like this. So you have a cycle. One edge of the cycle can be repeated, and you have as many loops and co-loops as you like. You can also have uniform matroids with additional loops and co-loops. So same game as before. And I don't think I have to explain what this class is in more detail. And then there's a last and fourth, little bit more complicated class where things go on. But they look like sparse paving matroids. If you have a connected thing, and if they're disconnected, then there's a special type of this partition matroid. Okay, but here, not all I promised holds. I mean, the Tutte polynomial will be universal on this class, but the rank is low, so there's no hope that you can express every Tutte polynomial as a linear combination of those. They're just too few. Okay, why do I show you 4 different classes? Okay, maybe one of them was in particular interesting. Maybe you're interested in graphs, then a second one is interesting. But the other 2, I don't see too much in them, but I all need them for the final result, right? So I want to have an inclusion-wise maximal family, which is closed under taking minors, under taking duals, for which the Tutte polynomial is universal and relative. And then I promise you, or the theorem promises you, that you have seen all possibilities. And of course, if you take a subclass, they will have the same property without the maximality. So the elementary split matroids are an example, the uniform matroids with additional loops and co-loops, the graphic Schubert matroids, and then this last family with sparse paving matroids and these special partition matroids. Okay, let me use the rest of the time to show you how this proof will work. And it's a little bit of luck. So we look at the matroids of rank 2 on 4 elements. There are not so many. There are 7 of them. And you compute the rank of their Tutte polynomials. You will see the rank will be 5. Okay, so you need kind of canceling 2 relations. There are 2 relations you can find easily between the Tutte polynomials. So I've written down both of them. And I picked them carefully. I picked them in a way that they do not have a counterpart when I look at the G invariant. Okay? There's one relation among these polytopes, the one I just showed you with the 2 Egyptian pyramids, which also is there for the G invariant. I don't pick that one, I pick 2 others. And I want somehow to break them, because as long as they hold, something bad happens. I can't have something which has maximal rank. Okay. And how do I break 2 things? Either pick a minor or a matroid which appears in both of these relations, or I take something that or several matroids so that both of these inequalities don't hold. So there are all the options. I pick either U12 with an additional loop and co-loop. I will end up at split matroids, and you see that this matroid appears after the equation in the first line and before the equation in the second line. So if I remove it, these equations are not there anymore. And in all other cases, I have to exclude 2 minors. So either this elementary Schubert matroids and the direct sum, or the uniform matroid and the direct sum, or, and this is the only tricky part, right? If I remove a loop plus U23, then because of this duality property, I'm also forced to remove U13 and U11. And I just showed you that all these 4 classes you get are indeed classes where the Tutte polynomial is universal. So kind of by magic, we are done. And this is a nice proof. If you, of course, remove the assumption that you're closed under duality, you have to do more, and the analysis gets more complicated, and I couldn't perform it because I don't know what happens in higher ranks. Okay, let me end here.
Thank you. Any questions?
So what's special about the Tutte polynomial here?
I mean, Tutte polynomial is, of course, very, very interesting. That's why we picked this as the example. And there were also some open questions by about this. So, I mean, yeah, so that's why we did that case. But it's true, and I invite everyone to look at other invariants and play the same game, I mean, you wonder why should you do this? But I would assume if you have an interesting invariant, you should also get some interesting class on the other side. I mean, I would say there's some noise. You see these other three classes here, but one of the classes is interesting, and that should happen also with your favorite invariant. And I assume you can also try to play the game in the other way around. You start with a minor class, which has to, or the G invariant, so if you take the image under the G invariant, if your class is a subgroup there, then you can ask for an invariant which cuts out exactly this as a minor. And I think this is also a very interesting question.
Any other questions? I was wondering whether this kind of thing has been generalized, or I don't know whether it's a good word to generalize, but there are like interlaced polynomials or other polynomials, analog of Tutte polynomial in other contexts, whether people study.
This is the first work who studies this special thing of restricting the class of matroids such that we become universal relatives. So this is the beginning, but you're invited, and you can also talk about it to study other things. And actually, there is another invariant. So there's a generalization of Tutte polynomials to chain Tutte polynomials. You can play the same game. So, there's a paper on it by Max Wakefield. And the day I published this on the archive, he already sent me an email and asked, what is about the chain Tutte polynomial? And I could answer that. I have some notes on that, and we will probably publish this soonish. There also, the answer is pretty nice.
All right. Any other question? So if not, no, do you want?
I was just curious if you can classify the invariants for which there's a unique class.
That would be very interesting, but I also don't know how hard this becomes. But yes, it's an interesting question. I agree.
Okay, cool.
All right. Then let's thank the speaker again.